So, now I will demonstrate measurement of resistivity of a metal and a semiconductor as a function of temperature. So, this is very simple experimental setup. So, I will show you that sample. So, this is a sample holder, it is made of copper. We will use liquid nitrogen for cooling this sample. So, here we have used the copper stripe because this will put in the vapor of the liquid nitrogen, and this copper stripe will be cooled because it is the thermally conducted and it will reach to the sample. Now, here you can see just sample is inside, it is a metal, I think some foil we have taken, it is maybe aluminum foil or exactly I do not know, but some foil we have taken for the as a metal. So, inside the sample is there, and then this white part you can see, this basically thermally, this electrically isolated from this top stripe. Again top stripe we have used copper because the temperature has to reach to the sample. So, this sample is in touch with this copper, so that when copper will be cooled in liquid nitrogen vapor, then that sample will have the same temperature. Okay. Now, here it is a metal, and metal have very small resistance, and change of resistance with temperature that may be also very small. So, here we have used 4-probe method. Okay. So, here 4 wires you are seeing. So, that means with sample this 4 connection, outer 2 we will use for current and inner 2 we will use for measuring the voltage drop. Okay. So, this is exactly the linear 4-probe method, as I have used this 4-probe method in case of magnetic resistance measurement. So, same for linear 4-probe method we have used for metal. Okay. Now, other side we have put the semiconductor. Again you cannot see the sample. Here again you can see this copper stripe. Okay. Now, below this copper stripe this semiconductor material is there. So, again why we use this copper stripe on top as well as in this bottom, means this main stripe. Okay. And in between we have kept the sample. Reason is that this sample will reach to the same temperature of the copper stripe. So, copper stripe is a very good thermal conductor, because of that we have used this copper stripe. Okay. So, from this semiconductor we have taken these 2 connection, we have taken here, you can see these 2 connection we have taken. I should not disturb much. So, these 2 connection we have taken. So, here basically we have used 2 probe, means from these 2 connection we are, so we are applying current, constant current through these 2 connection, as well as these 2 we are measuring the voltage between these 2 connection. Now, 2 probe you know that contact resistance will contribute in the total resistance. So, but since the semiconductor resistance is higher, so contact resistance can be maybe negligible compared to the sample resistance. So, that is why here we do not need to use 4-probe method, 2-probe method is good enough. So, that is why here 2 connection, for the semiconductor. Okay. So, 2-probe method. Now, here these 2 connection, is basically this is the platinum resistance, this is the platinum resistance here. So, we have taken connection, these two outer connection is basically for as a thermocouple. Okay. So, resistance of this platinum will change with temperature. Now, actually measuring the resistance of this platinum, we can tell what is the temperature. Okay. So, from calibration curve one can find out. So, this I will put inside this one. Okay. This basically thermally isolated tube. Okay. So, I will just fix it. Let me check the hole. Yes. I will fix it. Yeah, I think one has to do it. So, I have opened it to show you, but generally we do not open. So, now you see this in experimental physics 1, I showed you the screw. Okay. So, now it is useful. Okay. So, I have fixed it with this rod. Okay. And all connections are coming out. This rod is, so here this Teflon is there. So, through Teflon electrically isolated. Okay. So, these all wires are coming out. So, how many wires are coming out? So, for metal 4 wires, 4 probe method, 2 for constant current and 2 for measuring the voltage. Okay. So, these 4 wires from here, these 4 wires is going to this setup. Okay. These 2 are here, these 2 are here, this is the constant current source. So, these 2 for 4 probe for metal. So, these 2 are for the passing constant current to the metal, and other 2 wire we have connected. You can see we have connected basically other 2 wire we have connected here. It is the basically micro voltmeter. Okay. So, it will basically measure the voltage drop of the metal. Okay. So, this 4 connection for metal and 2 connection for the semiconductor. As I told, the 2 probe we are using. So, these 2 connection, these 2 we are giving here this constant current source. Here also I need constant current source. So, current will pass through these two probe to contact, and from these 2 contact itself we will measure the voltage. Okay. So, from this same connection we have taken for the voltmeter. Okay. Here this is the voltmeter, digital panel meter VDC. So, voltage, DC voltage. So, this is the voltmeter. Okay. So, this part is for semiconductor for current and voltage, this part is for metal for current and voltage. Okay. Now, so these 4 wires and these 2 wires, 6 wires and 2 more wires, as I told, this platinum resistance is there for measuring the temperature. So, these 2 we have connected here is a multimeter. Okay. So, multimeter here basically it will show the change of resistance of the platinum platinum. So that platinum resistance will change with temperature, and there is a calibration table supplied by the company. So for different platinum resistance, what is the temperature? So that calibration chart is available with us. So this is the calibration chart. This is the calibration chart. Okay. So this is ohm. This is the resistance at different temperature. So this voltmeter will tell us the resistance of the platinum, and corresponding temperature we will get from the table. Okay. So, so what we have to do? We have to basically initially let us just start the experiment. When we will start the experiment, let me switch on everything. Let me switch on, and this for this one. So I have switched on this setup. Okay. Now here this for metal, so current is 0, constant current passing to the metal, it is 0. So here naturally voltage has to be 0. So here 0 adjustment is there, that voltage drop should be 0 because current is 0. Okay. So I set at 0. Okay. So this for metal. Now this for semiconductor. So here current 0, so here I do not have adjustment, it is the 1.5 negative it is showing. So I do not have option to adjust, but let me check it. No. So it's some value it is showing, but so this I don't have option to make it 0, but this one can just keep note. Okay. So because this value will be negligible compared to this other our data. Okay. So now here it is showing 108.26. Okay. This resistance, it is 200 ohm range. So 108.26 ohm resistance, platinum resistance. So for that, what is the temperature? From this chart I can tell you. So from this chart I can tell you. So here it is 108, that means it's I have to go 108. So I have to go 108 here. You see here 108.18, 108.56, 57. Okay. So here you see this temperature between 21 and 22. Okay. So temperature is average temperature, you can tell that's 21.5. Now is the winter time, is a December end. Okay. So room temperature is around here 21.5. So I have to note down this. So we have to make table. So this, what is the resistance of the thermometer, whatever we are getting here, and corresponding temperature from the chart we will note down. Okay. So now in which way we will vary the temperature here. So here also we will note down this zero current. For that, what is the voltage? So if you have any adjustment, just adjust it, otherwise just keep note. Here also for semiconductor, zero current and negligible whatever the voltage, just keep note down, because this is the error, we do not have adjustment. Okay. So now how I will vary the temperature in this experiment? So what we will do, we will put liquid nitrogen in this tube, and liquid nitrogen. So this we kept this sample is up, okay. So we will put liquid nitrogen will be the at the bottom of this tube, okay. Then it will generate vapor, and this sample will be in that vapor, and temperature, it will reach to the liquid nitrogen temperature. It takes time. So, and then we will allow to for natural heating up of this, because surrounding temperature is 21 degree centigrade, and inside temperature will be liquid nitrogen temperature. So, with time what will happen, this it will be vaporized, this all nitrogen will be vaporized, and there is a due to because of the high temperature difference between the environment and the sample place, okay, that is at liquid nitrogen temperature, and environment is liquid nitrogen temperature is basically it's 77 Kelvin. That means it is minus or nearly is a minus 200 degree centigrade, okay. 173 and 77, so 4 is a minus 196 degree Kelvin. So approximately it's a minus 200 degree centigrade, and environment is plus 20 degree centigrade, 21 degree centigrade. So because of the high difference of the temperature, so thermal, so there will be thermal conduction, okay. So this sample place will be, because of this thermal conduction, so this temperature will from environment temperature will go to this system, and as if it will heat up, slowly with time. So that natural heating up, that this procedure will use, but in very good system generally people keep the heater, okay, and this should be, that is PID control, means it's called proportional integrated and differential PID control. So, but that arrangement we do not have. So, in that case you can control the temperature and keep stable for any temperature. So, that arrangement is costly. So we do not have here, but here in natural way we will heat up the sample from the liquid temperature to the higher temperature with time, okay. So now what we will do, let us I think I should put liquid nitrogen, it is this one, let us put liquid nitrogen. So if I put some current here, metal, it's a ampere, so it's if I apply, this is say 0.1, 0.2, in this case let me apply 0.2 ampere current, 0.2 ampere current to the metal, okay, corresponding voltage at this temperature we should note down, okay. And now here I will apply current, say in case of this is 0.4, say 1 milliampere current I will put here. One milliampere current I have put here. So, corresponding voltage at this temperature you can see here. Now, when I will put liquid nitrogen, temperature will change, will lower. So, what we will expect? So, this current in both cases should remain constant, okay, and this voltage resistance, if whatever the resistance will change, that we will see in terms of voltage. So, in this case, in case of metal, when temperature is lower, resistance will be lower, okay. So, here we are expecting that resistance temperature lower, resistance will be lower, so voltage drop will be lower, okay. So, here we are expecting that voltage will decrease, okay, in case of metal, okay, because V by I, that is the resistance. And in this case, in case of semiconductor, we will expect that temperature decreasing, then resistance will increase, and voltage drop will increase, okay. So, here we will expect that the voltage will increase, okay. So, here voltage will decrease and here voltage will increase when we will put liquid nitrogen. Let us see whether it happens or not. So, I think Mr. Prashanto, he takes care of this solid state physics laboratory. So, one has to put liquid nitrogen very carefully. As I told, this temperature difference of our body and the liquid nitrogen, that is that temperature difference is more than 200 degrees centigrade. So, it will burn your hand or leg if this liquid nitrogen falls on your hand or leg, okay. So, one has to do very carefully. So, what we have done, we poured the liquid nitrogen and they just covered up with some, it is a covered, very cold, it is very cold, okay. So, now here you see, in this case what you are seeing, whatever the value was there, that decreased, and here whatever value was there, now it is increased, you know. So, earlier it was 0.55 something, some reading was there, and now it is increased 1.013. So, as I mentioned that in case of semiconductor, resistance will increase when temperature decrease. So, voltage will increase, that has happened here, and in this case some value was there, now it is, you see, it become just 0, okay. So, at liquid nitrogen temperature, now you see here, as I told, this reading was 108.26, now it is 21.1, this platinum resistance, it is 21.1, and for 21.1, what is the temperature? From this chart we will see this is the 21.1, here you see 21.08 and 21.51, in between temperature is 94, 93, 94, okay. It is the minus sign, here minus is given, minus 220, minus 219, etc. So, it is a minus 194, okay. So, as I told, liquid temperature is minus 196, this 77 Kelvin. Now, already our sample is at 194, okay, because this is 21.2. Now, what is the value? It is the 21.2. So, it is exactly, is not at the liquid nitrogen temperature, or so here you see this platinum thermometer is a very good thermometer for measuring temperature. So, just simple, just using this voltmeter and using the voltmeter and a piece of platinum wire we have used, okay, and just we are measuring the resistance. Now, from calibration curve, okay, we are able to tell this what is the temperature. So, these are another type of thermometer, like thermocouple we are using for measuring temperature. Similarly, platinum thermometer we are using for measuring temperature. So, it is the, so it is the 21.1, okay. So, it is the temperature is 194 minus 194, corresponding you these are in centigrade. In Kelvin it's around I think 79 Kelvin. In Kelvin it is a 79 Kelvin, okay. So now we have to wait. I can open it now. What I want the increase of the I want to increase the temperature, okay, of the sample. I do not have heater, so in natural way I want to just so I will allow to vapor go out. So I think almost all liquid has vaporized, slightly some. So what will happen with time? It will change the temperature very slowly. At least it will take more than an hour, okay, to come up at the room temperature. So here I will look at this change of the resistance of the thermometer, corresponding temperature I will get, and for that temperature what is the voltage from here and here for metal and for semiconductor I will note down, okay. So now it will take time. Now it is still at the same temperature 21.1. Now it is started to change. No, I think this connection disturbed. So I think just here I was able to show you that it was at room temperature. What is the voltage for metal and for semiconductor for particular constant current. So voltage, when I decrease the temperature at liquid nitrogen, so voltage will increase in case of semiconductor and voltage will decrease in case of metal, and that's happened, okay. Now temperature will increase, this voltage, in this case voltage will decrease, in this case voltage will increase, okay. So with time there will be change of temperature. So we have to note down this temperature from this thermometer, platinum thermometer, and corresponding voltage for metal and this semiconductor we have to note down for particular constant current for metal and semiconductor, that we have to note down. Then just we have to divide it, we have to divide the voltage by that constant current, and then we will get resistance. Now resistivity, how we will get? Resistivity we will get, so data will be supplied to you, rho equal to R L A by L, okay. So what is the dimension of the sample, that will be supplied to you. What is the, so A and L you will know, and then resistance you are measuring from V by I, okay, at different temperature. So you will get the corresponding resistivity at different temperature. So then plot resistivity at different temperature, and from that plot you can see the nature of the change of the resistivity as a function of temperature, and fitting that curve you can find out the temperature dependence of resistivity for that material. So for metal, but for different material. So, it's a it can show so it will show the different kind of variation. It's a always increase, but the slope etc. Linearity. So, it's a so exponential this, as I told this, it is a polynomial of polynomial function. So, other higher terms will contribute also. So, it will, whether it will contribute or not, whether that will depend on the type of metal, as well as it will depend on the range of the temperature. Okay. So, one can study the temperature dependence of metal and semiconductor from this simple experiment. So, I think still it is 20. So, it will take time initially. I think it start to warm up, it at least it will take half an hour, and then after that it will just drastically. So, I think still some liquid nitrogen is there. So, that is why it is maintaining the temperature at the same temperature, because these value are still same. So, this I explained, and just now you have to note down the data with time. Okay. So, as temperature will increase. So, I will stop here. Thank you.